talk is Hermitian sums of squares modulo Hermitian ideals. So the outline of the talk. First, I'm going to introduce a problem, and the problem is writing a Hermitian polynomial is a Hermitian sum of squares modulo a Hermitian ideal. I'll then give some motivation for why someone might study this problem, and then discuss the context which led me to study this problem. And I'll talk about an idea from the recent context, which allows me to formulate some questions about Hermitian sums of squares modulo Hermitian ideals, and then I will present my answer to some of these questions and discuss why I think they're important to the main problem and what they could bring in the future. So first, the problem. Before I can formulate the problem, I need to talk a little bit about Hermitian polynomials. I let C and Z bar be the algebra of polynomials in variables z1 through zn and z1 bar through zn bar with coefficients in C. So Z denotes the z's collectively, and Z bar denotes the Z bars collectively. I can write a polynomial here using multinomial notation. So you have the coefficients, and the alpha and beta are then n tuples of natural numbers, and we have a separate multinomial index for the z's and the Z bars, and all but finally many of the coefficients are 0. So this algebra has an involution given by conjugation. So we conjugate the coefficients, the bars go to their counterparts in the z's, and the other way around. So now we say a polynomial is Hermitian if it's fixed under the involution. Some quick information about Hermitian polynomials. They are real valued on Cn. So if I plug in a point in Cn, since it equals its conjugate, it will be a real number. And the coefficients satisfy this Hermitian property. So because they're real valued, it makes sense to say if a polynomial is positive at a point or strictly positive at a point or on a subset. So I'm going to use the term positive for greater than or equal to 0, and strictly positive when I mean greater than 0. And I put a little h here to denote the collection of the Hermitian polynomials. Some quick information about this collection. It's an R algebra isomorphic to Rxy with the standard correspondence. So x is n, there's n x's and n y's. So these are the standard object that I work with, Hermitian polynomials. And we say an ideal in this algebra is called a Hermitian ideal. So now we need Hermitian sums of squares. Polynomial in only Z we will call a holomorphic polynomial. And a Hermitian polynomial of the form holomorphic times holomorphic polynomial bar is called a Hermitian square, and a Hermitian polynomial of this form is called a Hermitian sum of squares. And I let sigma squared sub h be the collection of Hermitian sums of squares. We're going to think of elements in complex space as column vectors, and we denote the bracket by v star w, the standard Hermitian inner product, and the convention here is that it's conjugate linear in the first component. And one more term, a holomorphic polynomial map is a map whose components are holomorphic polynomials. And this is convenient to write a Hermitian sum of squares as the square norm of a holomorphic polynomial map. So H here, the components are the L holomorphic polynomials. Any questions so far? Right. So here's the problem. We take a Hermitian polynomial and a Hermitian ideal. Under what conditions on F I, can we write F as a Hermitian sum of squares plus something in the ideal? If such an identity exists, we say it's a Hermitian sum of squares modulo I. We write it like this. So what's the first thing we could say about this problem? First, we have the so-called trivial necessary condition. If, suppose we have a Hermitian sum of squares mod I, and what about points where G vanishes? Then F must be positive. So F has to be positive on all points in the zero set of the ideal. And we could ask, is this condition sufficient? It is not sufficient. So here's an example. Consider this Hermitian polynomial here and this ideal. So the zero set of this ideal is C, and since Z plus Z bar is twice the real part of Z, this polynomial is positive on C. And if F is a Hermitian sum of squares, then the zero set of F is a complex algebraic set given by the zero set of these polynomials. However, the zero set of F is the imaginary axis, which is not a complex algebraic set. It has to either be finite or all of C. So the trivial necessary condition is not sufficient. So now I'm going to give some motivation for why one might study these types of problems. And we start with complex algebraic geometry. So the fundamental theorem of algebra allows us to count roots of polynomials. A polynomial of degree n with complex coefficients, how many roots does it have? It has n roots. And a counting multiplicity. And if the coefficients are real, they occur in pairs. And this then leads to the Hilbert-Nullstellensatz as a fundamental result of complex algebraic geometry. If we have an ideal in a polynomial ring over an algebraically closed field, then these conditions are equivalent. F is 0 on the zero set, and F to some power is in the ideal. Right, so this is leads to the notion of the radical of the ideal. And then it develops into this big connection with commutative algebra and the Zariski spectrum. So starting with our commutative ring, we have the points being the prime ideals. And so this condition says if x times y vanishes, then x vanishes or y vanishes. And we have our topology being the open sets, non-vanishing sets of functions, and we have our sheaf of functions given by localization, and this point here is that the classical points are in bijection with the maximum ideals. So this topology then doesn't relate to the Euclidean topology of complex space. And at some point, you might ask, can we get a implicit function theorem? And, well, this ends up being a lot of work by Grundig on the Etal site, and that's where I stop. Now to the real world. And again, we begin with root counting. So, Descartes' rule of signs, Sturm sequences, you have a real polynomial, and you can sort of count the roots, get information about the locations of the roots without computing the actual roots. And I still want to say, suppose instead of an algebraically closed field here, what if we have R, the real numbers? That's a good question. So a couple of facts about ideas of real algebraic geometry that are different than complex algebraic geometry. Real numbers are ordered, and then we're allowed to say if functions are positive. And if we have a collection of polynomials, we can determine a semi-algebraic set. So this could be like the interior of a square or a polygon. And say one reason I would say for the late development of real algebraic geometry is that there's this like behavior that appears wild if you have only habits of complex algebraic geometry. So what's possible is you could have irreducible varieties which are non-connected. So here, this cubic curve has two components, and one of them is a single point at the origin. You have even different components of different dimensions. And one of the, it wasn't even known if a real variety has finitely many connected components until Whitney in 1957. And one question is every positive polynomial a sum of squares of polynomials? So if you take a sum of squares of polynomials, then that will always be positive, and we ask the converse. And the answer is no, and Hilbert gives a non-constructive proof of the existence of such polynomials, and it wasn't until 1967 that Motzkin first wrote down an explicit counterexample. So you can use, say, the inequality of the arithmetic mean and geometric mean to show that this is positive for all x, y, and R2, and you can argue by, say, some combinatorics with the monomials that there's not possible to have a sum of squares add to this polynomial. And so the question was revised. Okay, maybe not a sum of squares of polynomials, but if the polynomial is positive on Rn, then is it a sum of squares of rational functions? And it's the solution of this problem which leads to some of the foundational results of real algebraic geometry. Before I talk about those results, I will give you the answer to that other question, the Null-Stellensatz over R. Here's one version by Krivine in 64. So if you have a ideal, so x again is multiple variables, then these conditions are equivalent. F vanishes on the zero set, and there exists an identity like this. Negative f to the 2m is a sum of squares plus g. So g is in the ideal, and we have a sum of squares plus g. And I won't formulate the positive Stellensatzes. You could have similar theorems with f greater than or equal to 0 on z, or f strictly greater than 0. And I just want to point out that you have some sums of squares coming up and some powers. They're a little different than the Hilbert Null-Stellensatz. Now for the solution of Hilbert's 17th problem. So Art and Schreier in 1927, they introduced the concept of real fields and real closed fields. So a field is real if there exists an ordering. The real numbers are a real field. And it's real closed if, when you adjoin the square root negative 1, it becomes algebraically closed. And this here is probably the important idea they have. If we have a real field, and we have a element which is not a sum of squares, then there's some ordering of this field in which it becomes negative. So there could be multiple orders on the field. For instance, the field of rational functions has multiple orders. If you have a point, then you can evaluate your rational function at the point, and you can have an ordering there. There are also multiple orderings that are related to like asymptotic limits as you approach the point. So like 1 over x could be infinitely large if you choose the ordering by evaluation at 0. And then Tarsy, in 1929, he proves that you have quantifier elimination for first order theory of R. This could be any real closed field, actually, in this language. And what's important out of that is this idea of the Tarsy transfer principle. So if you had a first order sentence over a real closed field, then if it's true, then it's true in all real closed fields containing that real closed field. So you can go, say you have a sentence over R, and you could go to a larger real closed field, such as the real closure of the field of rational functions, solve your problem using the function theory, and bring it back down to R. And they give this notion of a real prime ideal. So if you have a sum of squares in the prime ideal, then each of those is in the ideal. So it's like the sum of squares vanishes, then each of them vanishes. So these together end up being the results that solve Hilbert's 17th problem. I'm going to attempt to explain down here a modern proof of it with these kind of combined. So an ordering of an algebra satisfies these properties. So this is like the sum is supposed to be, for instance, if A is R, then P would be the positive numbers, including 0. Satisfy these properties. If you add two positive numbers, it's positive. Multiply two numbers, it's positive. The number is either positive or negative. And if you take the intersection, so where it's positive and negative, that's like the zeros, then it's a prime ideal, so it has some geometric meaning. And you get this data for the real spectrum, where the points now are orderings, and we have this topology for each function, element of the algebra. The open set is where it's positive. So it's basically the orderings in which this is positive. And this idea here, now the classical points correspond to maximal orders. So all the functions which are positive at that point, that's now a maximal order. And so the idea for Hilbert's 17th problem, we're trying to show if a positive polynomial is a sum of squares of rational functions. So the field of rational functions, we suppose it's not a sum of squares in that field. Then we have some ordering on the field of rational functions in which that polynomial is negative. And sort of then that ordering, you can extend it to a maximal order, which is like evaluating at a classical point. And you can use the Tarsy to push it back down and find a point in Euclidean space where the function is now negative. Okay. So we go from complex to real, and now we move to the Hermitian world. So the first result, say, goes back to Sylvester. If you have a Hermitian matrix, so A star being the conjugate transpose, and then there exists a real diagonal matrix D and a unitary matrix U, such that A is diagonalizable by U into D. So the real elements on the diagonal are the eigenvalues of A. And of course, Hermitian operators are incredibly important. In physics, Hermitian operator corresponds to a physical quantity. But I also want to make this sort of analogy with starting from the root counting, which begins with Hermite. And this method is as follows. If I take a holomorphic polynomial of degree n, define this polynomial. So this, we conjugate the whole thing, and then we conjugate the z's. So this only conjugates the coefficients. Consider this function. Now, if you set u equal to v, then the numerator vanishes, and so we can divide out and write it as some function, expand it. So now the context, which leads me into this problem. So first, we talk about the sphere. Now I denote the odd-dimensional sphere here, and this theorem, equivalent Glen-D'Angelo theorem, says strict positivity on the sphere implies that F is a Hermitian sum of squares mod the ideal defined in the sphere. Glen and Glen-D'Angelo both give analytic proofs, Glen with the Fock space and Glen-D'Angelo with the Bergman space. And I'll mention that the case n equals 1, the unit circle, is a very classical result by the name of the Riesz-Fedger lemma. And it's about the positive trigonometric polynomials on the unit circle. And in this situation, strict positivity can be relaxed to just positivity. We're going to see more about this later. And in 2006, D'Angelo asks if before he asks that, he says, okay, the sphere is the prototype of a pseudo-convex boundary in complex space, and maybe we could generalize this to any pseudo-convex boundary. So he asks if our Hermitian polynomial is positive on the pseudo-convex boundary, is a Hermitian sum of squares modulo the boundary. And the answer to this question is no, and it lies in a paper by Putinar and Scheiderer in 2010. The title of the paper is Hermitian sums of squares on pseudo-convex boundaries. So I want to talk about the idea that they used to construct this counterexample, and then show how I believe that's an incredibly important idea to solving the problem of Hermitian sum of squares modulo Hermitian ideals. So what is this idea? First, we need an even earlier idea, the idea of a Gram matrix. And here, I introduce the terminology that a matrix is positive if this product is always greater than or equal to 0 for all vectors V. We denote this by A greater than or equal to 0. Now, suppose I take the matrix with these columns, so pick some vectors and form the matrix of those columns. Now, if I take B star B, this is the matrix of inner products. And we call this a Gram matrix. The fact is that every Gram matrix is positive. If I form the product, and then I can write this as the squared norm of the vector VV, and that's always positive. Turns out that actually every positive matrix can be written as a Gram matrix, and this characterizes positivity. So for Hermitian matrix A, these conditions are equivalent. A is positive, A is B star B for some matrix B, and I put another one here, all eigenvalues of A are positive. So we can see that from the spectral theorem. We could make a whole list of equivalent conditions for positivity if we wanted. I only put 3 here. And we use this idea to obtain further necessary conditions for Hermitian sums of squares beyond the trivial necessary condition. So one thing to note is that for polynomials here, we can actually evaluate z and z bar independently. Now suppose I have a Hermitian sum of squares block the ideal. What does that mean? The Hermitian polynomial is a squared norm of a holomorphic polynomial map plus something in the ideal. So again, what makes this vanish? Suppose I have points such that the pairwise evaluations vanish for all points in the ideal. Then F will agree with pairwise inner products. So this matrix agrees with this matrix. This matrix of pairwise inner products. And we've just seen that this matrix is positive. So we can conclude if F is a Hermitian sum of squares mod the ideal I, then this matrix of pairwise evaluations is positive for all collections of points that satisfy this property for the ideal. So this is the idea. For notation, if we have the points in the polynomial, let's denote by gram of f, evaluate on the points P1 through PL by this the matrix of pairwise evaluations. So let's revisit this example. So I have the polynomial and the ideal. Let's choose these 2 points. And if I look at the gram matrix, I get a 0, a 1, and a 4. And 1 plus 1 squared is 4. This is not positive. So one reason is its determinant is negative. I didn't mention that as the equivalent condition, but we can calculate value values. So by the idea, this means that f is not a Hermitian sum of squares. So already we can reprove some of our ideas using this new idea. And here's another example. Consider z to the n, z bar to the n minus 1. Let's take omega to be a primitive root of unity and take a point on the unit circle. So this will denote the unit circle in C. Then I take the point and multiply it by the root of unity, rotate it around the circle. I have n points, and the pairwise evaluations of R on those points vanishes. So what does the idea tell us? It says, if I have a Hermitian sum of squares mod this ideal, then this gram matrix must be positive for all points on the circle. The main question I ask is this sufficient? If I start with this, can I get f to be a Hermitian sum of squares? That's my question. Can I show that this positivity condition applies f is a Hermitian sum of squares mod this ideal? So another thing that Pudnar and Scheider do is they classify all the Hermitian ideals such that they basically ask the question, when is pointwise positivity sufficient? And because the Quillen-Catlett-D'Angelo theorem needs strict positivity on the sphere, they use only strict positivity. And by applying ideas from real algebra and real positive Stauensatz in the correct setting, they're able to classify these ideals in terms of this compactness property here, the Archimedean property. So this sort of says that the zero set is bounded. And another point is that the n equals 1 case here is just the circle on its own, and but yeah, pointwise positivity is sufficient from this Riesz-Fedger lemma that I mentioned earlier. So I'm actually going to use ideas from a generalization of this to connect to solve this problem. And I want to make a note here that if we look at the zero set of this polynomial for z and c, it's still the circle, which is compact. But if we look at z and z bar as independent, then this zero set in C cross C is more interesting, right? We have all these points that we found in the example where we computed the conditions, right? So for n equals 1, there's no points off the diagonal, but for n greater than 1, we have points off the diagonal. So I'm going to give an example where for n equals 2, where I have this condition and I get this. So it shows that I'm on the right track. So for n equals 2, consider this Hermitian polynomial. And I want to talk about how we can write these in a matrix notation here. So again, the star means conjugate transpose. So right, we have a 10 with the 1, 1, a 2 with the z. So we get a 1, 2, z. And same thing here, we have a 2 z bar. So if you look at this matrix here, it's not positive. And that implies that F is not a Hermitian sum of squares. And if I compute the Gram matrix of F on a pair of antipodal points, get this, and we can compute that this is positive. That's what we wanted. It's okay. It's the Gram condition is satisfied, and it's not a Hermitian sum of squares. And when I add 5 times the polynomial, I land in the sum of squares. So I add the 5, so I have to add 5 to the z squared, z bar squared, and subtract 5 from the constant term. So I get a plus 5 here and a minus 5 here. So it does this modification. Now we can check that this matrix is positive, and therefore F is a sum of squares mod the ideal. So I'm going to give the answer to that question. I'm first going to talk about some ideas from the n equals 1 case. So take a polynomial, not necessarily a Hermitian, and I can write it in this matrix notation. So C, psi sub m of z is this vector of monomials. And as we just saw in the previous example, I can write every polynomial in this way. And the idea is if I integrate around the circle, I get the trace of the coefficient matrix. So we're integrating these like e to the, each of these becomes like an e to the I j minus k theta, and then when you integrate that around, it equals 0 unless j equals k. So we'll get the sum of the diagonals when we do this integral, and therefore it's the trace. Okay. So suppose I write Hermitian polynomial in matrix notation. So when I reduce the coefficients mod this ideal, then the diagonals collapse. So this will add with everybody on its diagonal. Go down. And I can find a unique representative mod z bar minus 1 of this form. I'm going to call a polynomial of this form a trigonometric polynomial with the data a0 through am. So I'm just finding a nice way to say I have a polynomial with this form, and then the others are the conjugates. And suppose I have a holomorphic polynomial, and I take its square norm, the matrix looks like this. Now what happens when I reduce mod z bar minus 1? I would get that the trigonometric data is related to the h's like this. So I add my holomorphic polynomial, I square it, and then I reduce, and then I have that the a, like a1 is the sum of this first sup diagonal, and the a0 is the sum of the diagonal, and so on. And so these are equations characterizing the coefficients of h. So to figure out if f is a Hermitian sum of squares, it's enough to figure out how to solve these equations here. And it turns out that this system of equations is pretty widely studied, and it turns out that this equation has a solution for complex numbers h, if and only if this corresponding tuplets matrix is positive. So the tuplets matrix, meaning it's constant on the diagonals, and this is the idea. So we want to solve these equations, we have to make this, we can solve it if this tuplets matrix is positive. So we're going to try to go from like polynomial positivity to the tuplets positivity, which then lets us solve these equations, and then we get our holomorphic polynomial, which is equivalent. So how do we do that? So say I have a trigonometric polynomial with the data as before, and take a Hilbert polynomial, the same degree as the number of data. Then the claim is that if I take this integral, I'm going to get the tuplets form evaluated on W, the vector W being the vector with these numbers in it. So how does that work? So I mentioned that if we integrate this, we're going to get the trace of the coefficient matrix. So what are the diagonal elements of the coefficient matrix of this? Let's put them side by side. So now, let's think about a couple of them. So A0 has a 1, 1, and what can I multiply here to get on the diagonal? Well, it would only have to multiply by diagonal elements to land on the diagonal. So that's here I have A0 with a W0 bar, W0, and A0 again with a W1, W1 bar, and so on, WM bar, WM. And say what about the A1? So A1 has a Z and a 1. So he has to match with a Z bar, and if I add plus 1, 1 going down, so A1 will match with everybody on this diagonal. And similarly, A minus 1 matches with everybody up here, and same thing, and so on. So that's how we see the A1. It has a W0, W1, and there'll be another A1 here, and that will come with a W2, W1 bar, and so we get the doublets form. So this is one of the key ideas that I generalized to the general end case by figuring out how I can make the block tuplets form show up, and then I can use this generalization of the Riesz-Fezzer lemma to get the Hermitian sum of squares I want. So then, to the conclusion, if f is now positive on the circle, then we get the tuplets form as positive. So here, if f is positive, then this is positive because this is positive, and so then the tuplets form is positive for all W. And so that's how you go from polynomial positivity to tuplets positivity. Then we invoke this result that says if we have the tuplets positivity, we can solve these equations, get the h's, and then that gives us our Hilbert polynomial, which is then congruent to our trigonometric polynomial. So that's one proof of the Riesz-Fezzer lemma for positive trigonometric polynomials on the unit circle. There are many proofs, and this is the one I found was able to adapt to what I needed to do. So now for general n. So I can take my Hermitian polynomial. I can write them now in block matrix form. So I can group the monomials into a grid. And so psi of z would then be the vector of monomials 1, z, down to z to the n minus 1. So this whole thing is just a giant monomial vector, and I have it grouped like this. And again, I can reduce mod this ideal and move the blocks down, get a unique polynomial of this form. So a polynomial of this form I'm going to say is trigonometric mod zn z bar n minus 1 of degree n with this data. And I go for the same story. So suppose h is a holomorphic polynomial of the right degree. When I look at the squared norm of h, I can write it in a block matrix form. Now because this is a Hermitian square, this matrix is positive. And I have the same idea that now when I do the collapse, I need that, so f is trigonometric with the data of the a's, and again, ak has to equal the sum of the kth diagonal. Okay, so I'll tell you how to order diagonals. So I can write that sum of the kth diagonal, I can write that as trace t sub minus k cubed, where t sub k is the elementary block tuplets matrix with I on the kth diagonal. So the main diagonal is k equals 0, and to the right are positive diagonals. And so I just say I have the identity on the kth diagonal, and the rest is 0. And you can write the sum of diagonals in this way. So this is the sum of the kth diagonal of the block matrix Q. So I'm going to use the operator value RF theorem to formulate what I need. So here it says, if I have a Laurent polynomial with matrix coefficients, then these conditions are equivalent. A of C is positive for all points in the circle. The corresponding tuplets, block tuplets form is positive, and there exists a polynomial with matrix coefficients such that the Laurent polynomial factors like this. So I sort of got rid of the z's in here and just looked at the relations that were occurring between the a's and the p's and rewrote it in this form. So if I just have a sequence of matrices, then these conditions are equivalent. This tuplets form is positive, the block tuplets form. And there exists some positive block matrix such that the a's are the sum of the kth diagonal of that matrix. So that's what I wanted. And now the idea is, so if I can show the tuplets form is positive, then I get my Q, and then I get that it's a Hermitian sum of squares. So how do I go from the matrix positivity condition to the tuplets positivity condition? I first make a note that if I modify my elements in the ideal, it doesn't change the matrix positivity. Right, so if I have, okay, so this denotes the gram on the point rotated around. It's additive, and because the G is in the ideal, the gram matrix vanishes. All the point valuations are 0 for all points in the ideal. So, say without loss of generality, I'm going to assume my f is trigonometric on the ideal with the data. So what are we going to do? We're going to assume the gram matrix positivity for all points on the circle, and I want to use this to show that the tuplets form is positive. Then, from what I just said about the operator valued RF, this will allow me to factor or find the Q's that have the right relations to give me that f is a Hermitian sum of squares. So this is the hard part that I spent a lot of time trying to figure that out, and here's how you do it. So I had in the n equals 1 case, I had this idea that we could, if we integrate around, we get the trace. So I want to do an analogy of that, and I found out that I had to do this. I take the average of the gram matrix entries and integrate that around the column, around the circle. So using some cyclotomic identity, I can show that when I evaluate this functional on f, I get a sum of diagonal elements, which are divisible by n. So instead of the full trace, you only have some of them, once divisible by n. That's not related to this showing up in there. We get a bunch of more of them are 0. So this is the key idea, that for this functional, it computes the diagonal elements divisible by n. And I use this then to get a block triplets form of the polynomial to triplets positivity idea. All right, so here's what I want to do. I want to say, given some vector, two vectors and a matrix, I'm going to construct a polynomial such that the functional on that polynomial is the matrix product. I'm going to demonstrate it for n equal 2, and then say it generalizes. Here's the example. Let's take two vectors and the matrix, and I define these polynomials. So this is the polynomial where this is the coefficient matrix, and I define v wiggle and w wiggle by putting the coefficients sort of going backwards. Like this order is increasing, but the exponents are decreasing. I don't have a constant term. Then I claim that when I apply f sub 2 to this polynomial, I get the product. All right, let's see if we can figure that out. So because I have no constant terms here, when I multiply them out, there will be no constant term in this, and so I only need to consider this coefficient of z squared and z bar squared. Because as I mentioned, it's going to be the coefficients of the polynomial, and we're only going to get one for a sub 2, 2. So what is it? Let's start from here. With a0, 0, it has a 1, 1, and so it will have to go with a z squared, z bar squared. So it picks up a v0 bar and a w0 bar bar. And that's the a0, 0, v0 bar, w0. And say what goes with the a0, 1. So a0, 1 has a z and a 1. So it has to match with a z bar squared. So where do I get the z bar squared? So here's my z bar squared has a v0 bar, and my z has a w1 bar. So it gets that goes with that. And same for like this, we have the z. So like a11 will match with the w1 bar, and the v1 bar. And so we get the product here. So I then just do the general version of this. So if I have these vectors, I form the same polynomial, and then I have this. Exactly the same. And for positive integers, s and t, if I put this modification in front, I get a delta st. So if s equals t, then when you're multiplying by this z to the n, z bar to the n, if these are equal, then it's only shifting down the diagonal, and so it won't change the result. But say if they're different, then this box, it's going to move off the diagonal, and then when I apply f sub n, I have no diagonal elements, and I get 0. So now, I remind us again what we talked about, how to go from polynomial positivity to triplets positivity. We argue that we could take this integral and get the triplets positivity. So I do the same. I start with my trigonometric polynomial, and I take a vector of vectors, and then for each vector in the vector, I define those polynomials from the propositions I just talked about, and then I put them all together into this bigger polynomial. It turns out that that's the one that when I apply f sub n, I get the block triplets form. And then if we have the Graham matrix positivity condition, then when I apply f sub n, so this is going to be it's going to be positive for all the holomorphic polynomials, and that's going to imply that this block triplets form is now positive, which is what I wanted to do. And so I eventually got it all lined up, and it worked. So then I put it together into this theorem, where, again, I said without loss of generality, we can assume F is reduced mod the ideal, and we have these three equivalent conditions. So F is a Hermitian sum of squares mod the ideal. That implies 2. That's the idea of the matrix positivity conditions. And 2 implies 3 is what I just showed. We construct this f sub n, and then we construct all these polynomials in the right way, and then apply it, and we get the tuplet's positivity. And then I invoke the operator valued RF theorem to go that the tuplet's positivity gives me a block matrix Q satisfying all the relations I need to have that f is a Hermitian sum of squares mod the ideal. And then it's complete. So this is my theorem, and so we've written up the results. It's on archive, and we're communicated them to the other Hermitian sums of squares fans, and gonna try to submit this to some journals soon. So what could happen next? So I think the matrix positivity conditions are important. So say that we have the coefficients of a Hermitian polynomial. Just the coefficients form this object called a Hermitian tensor. And decomposing the Hermitian tensors into sums of rank 1 tensors, that's an active field of research. And people, they will start with the tensor and then consider the associated holomorphic or Hermitian polynomial. And it's just my opinion that they only consider the pointwise positivity, but they could consider the matrix positivity conditions. Because this problem is writing the Hermitian polynomial as the sum of squares mod the zero ideal. And so the zero polynomial evaluates to 0 on all pairwise evaluations. And so F, the gram matrix of F on all collections of points must be positive. So it's much more than pointwise positivity conditions are required. Right? We even saw the example z plus z bar squared did pointwise positivity, but not a Hermitian sum of squares. And I then just want to mention the main problem I still want to keep working on is are the matrix positivity conditions sufficient in general? And so suppose we're given some points. We have this map from the algebra of Hermitian polynomials to the collection of Hermitian matrices. I map the polynomial to its gram matrix. So this map is additive and multiplicative, but only multiplicative if we consider the product in the space of Hermitian matrices to be the Hadamard product, not the matrix product. And so what's the Hadamard product? It's entry-wise multiplication, and this sure product theorem says the Hadamard product of positive matrices is positive. And so if we pull back the positive matrices on this map, we get the collection of polynomials whose gram matrix is positive. And so it looks like that. And then this object P, it has these properties where it's closed under addition. Now it's closed under multiplication because of the sure product theorem, and it contains all sums of Hermitian squares. So I think these are starting to look like the orderings that we had for the real spectrum, and I would like to explore the possibility of developing some sort of Hermitian spectrum involving these objects as the points in the set, and recover all the known Hermitian positive Stahlensatz so far. The evidence I really needed to even start moving forward on that was I needed it to be true for the case of z to the n, z bar to the n minus 1. And it worked. So maybe it will continue to work. And all the known cases so far really fit in this framework that the matrix positivity conditions are actually sufficient. And that's it. Thank you.
Thank you. Are there questions? I ask everyone.
So Glenn, throughout this talk, you're restricting a lot to the circle, and you're also taking, there's a lot of Toeplitz operators lying around here. Is there any relation to the Toeplitz C-star algebra? Are the symbols of the Toeplitz operators you're constructing the original polynomial?
I'll be honest, I don't have any clue what you mean by symbols of the C-star algebra.
If you make your operators here as operating on L2 of the circle or L2 of the disk, I think we're talking about Bergen space here, although I'm not completely sure. There'll be an associated symbol, modulo compact. It'll be a continuous function. But I guess this is not the right question.
Okay, I guess maybe I would say that I don't think that I need to develop new tools to do this. So the Tarsy and the Orange-Schweier thing were like new tools that led to the real spectrum. I think they're all out there, and it's probably something related to a lot of these known ideas of operator theory. But I just would like to apply to the setting of just the Hermitian polynomials and have a nice polynomial theory, and looking at the zero sets as these real. So the zero set is like a real variety in complex space, but I'll try to make the point that more important is actually the off diagonal points.
More questions?
Yeah, I have another question. What's the shape of the squares living inside the polynomial? Should they also form a cone? The positive operators should generally form a cone.
Yes. It's a convex cone. Can I say any more than that? So it's closed under addition, multiplication. It's convex. It's closed under multiplication by real scalars. I guess maybe one kind of interesting thing is that, okay, so if I do,
what you're writing is not showing up.
no, that's too bad. All right.
It's conceptual.
Yes.
I want to say that every Hermitian polynomial is a Hermitian sum of squares minus a Hermitian sum of squares. And that's from the spectral theorem applied to the Hermitian coefficient matrix. And so when you have convex cones such that the cone minus itself is the whole space, that's I forget the word for it, but it's a nice property, and you don't have that in you don't always have that.
Yeah, these cones are still giving you orderings. I mean, that's where your capital P fits in.
Oh, so these are not orderings because P union minus P is not the whole thing, though. Because if you have 2 points...
Oh, right. It's only a partial ordering at one shoots.
Yeah, it's... So in the real case, we get... I had this condition that P union minus P is the whole thing. And that's because they, at a point, the function is either positive or negative, but now you can have this grand matrix with mixed signature or two things that are not comparable. You can have one positive, one negative eigenvalue, and so there's some more interesting things there.
Right. But, I mean, there's quite a lot known about having orderings which are partial orderings. In other words, you're not saying that any one term is greater than or equal or less than or equal to any other. You get a partial order on your whole space instead of a total order. So that might be worth looking at when you get in this more general case.
Okay. I'll take a look.
More questions? If not, please, I excuse our audience, and we remain just the committee.